All right, we have two more sections in chapter 12. Today we're going to take a look at a couple of really different concepts, but they're comprised of things that you've done before. We're going to look at tangent vectors and normal vectors. The words tangent and normal are familiar to you, but not necessarily in the way that we're going to use them today. So a little bit of setup for what we're doing and why, and it'll continue into section 12.5 as well. So this is sort of the motive behind the ideas that we're going to look at in these sections. In designing roads, this is an example, of course. You would want to avoid curves that are too sharp. So we have this idea of how sharp curves are when we look at things in two dimensions, right? You look at where things are differentiable, you look at tangent lines, and you talk about the sharpness and so forth. But it's a little trickier when you get into three dimensions on how to think about that. So in this section, and in 12.5, we will develop a measure of how much a curve is twisting or turning. At any point. And in part of the development of that is what's called a tangent vector, okay? And in particular, we're not just going to find a tangent vector, we're actually going to be finding a unit tangent vector. So what is the word unit telling us?
Magnitude 1.
Yeah, it's going to have magnitude 1. So this is, I don't particularly love the notation, but we're going to use it because the book's using it. It's capital T for tangent of a lowercase t. Yeah. T is a parameter, right? So think about parametric equations. We're going to be looking at that a little bit today too. And this is our position vector, r prime of t, divided by the magnitude of r prime of t. Okay, so that's what we're going to be finding. You know how to find derivatives. We've done that in recent sections. You know how to find magnitude, and so we're just going to put those two pieces together. We're going to actually make a connection to something we did back in chapter 11 as well in our next example, where we talked about parametric equations or lines to make this work. So let me give you the directions so that you can see where we're headed. So here are our two directions. Actually, I think I can start it over here. I can't finish it in one screen regardless, so I think I can do the first part in the first screen. So we're going to first find the unit tangent vector. And then for part B, we're going to find a set of parametric equations for the line tangent to the curve at t. I'm combining some direction sets that you're going to see into a single question because they they work well together. Our equation that we're going to work with is the vector, and we're just doing a two-dimensional one, but of course, just to extend it for the 3 dimensions, this is 3 cosine t, 2 sine t, and we're going to work at the point pi fourths. Okay, so to start with, we're going to take a derivative. So let's take a derivative. What is r prime of t?
Negative 3 sine t 2 cosine t.
Excellent. And can we find that evaluated at pi fourths? Sure we can. So what is r prime at pi over 4? So what is sine of pi over 4? What is cosine of pi over 4? Yeah, square root 2 over 2. So this piece right here is going to give you negative 3 square root 2 over 2. And then the second one is actually 2 times the square root of 2 over 2. Or we can concisely write that a little bit better as just square root of 2, right? So the second piece is square root of 2. Nice. Okay, so that's our derivative value. But that's not what we're trying to find, a derivative at the specific point. We're trying to find the unit tangent at that point. So the unit tangent takes the derivative of our position vector and it divides it by the magnitude of the position, right? At the value. And our value is at pi fourths. So we're finding this at pi over 4. So t of pi over 4. So our vector that we just got was negative 3 square root 2 over 2 and then square root 2. And then we need the magnitude. And we didn't find the magnitude yet, so let's actually find that before we even stick them all together, I think. So I think maybe we do need another screen still. I'm so close to almost done on the screen. Let's just shrink it a little bit and see if we can get away with it. Okay, so I'm going to find this, but I'd like to find my magnitude first. So let's find the magnitude. The magnitude of r prime of pi fourths. So I have the square root of the negative 3 square root 2 over 2 squared plus the square root of 2 squared. All right, so obviously the negative becomes positive, the 3 becomes a 9, the square root of 2 over 2 squared becomes what? One half? Anybody? Yeah? So we got 9 halves? Okay. Nobody wants to talk to me. All right, so I should have 9 halves and what, 2? So what is this value? Yeah, square root of 13 halves, or we could say that we have the square root of 26 over 2. Yep. That's my magnitude. So we're going to divide by that magnitude, square root of 26 over 2. Because I'm dividing it component-wise, right? So each of them is going to be divided by the square root of 26 over 2. So I can flip and multiply. So I have the 3 square root 2 over 2 times 2 over square root of 26. And then I have the square root of 2 times the 2 over the square root of 26. So obviously the 2's simplify. I would have the 2 and the 26 underneath the radicals would simplify as well. So this is a 13. And if I rationalize, I would have 3 square root of 13 over 13. I feel like I missed a negative. I did. I lost my negative here. Sorry about that. Okay, so that's the first piece. What's the second piece going to give us? Mm-hmm. So just in the same way, this 2 and this 26 give me a 13 here. And then if I rationalize, I have the 2 and then square root of 13 over 13. So this is the unit tangent vector. Okay, so combining some ideas that we've done, derivatives, magnitudes, and so forth. The other part of this, though, which I'll flip to my next screen, and let me just carry this unit tangent vector with us, because we're going to need it, is finding these parametric equations. So let me copy the pieces that we need over, copy to 3, didn't need that. We also had, as a reminder, so this is sort of part B, the original function, or vector function anyway, was negative 3, it was 3 cosine t to sine t. We're going to need that in a moment, so I'm going to go ahead and write that in as a reminder from where we came. All right, so we're trying to find parametric equations, and if you remember parametric equations that we had done before, one of the versions of them says very nicely that I can have x1 plus, it's like slope, right, a times t, and I have y is equal to y sub 1 plus the slope of y, and then it's bt. So it's the slope of y is the b. So the a and the b are the slope going on here. And the slope is coming from a tangent line, and we found tangents, right? It's the unit tangent vector that we just found. Those are slopes. So the a and the b are actually these values. So this is a, and this one is b. Okay? The other components, we can actually find the ordered pair x1, y1. It's an ordered pair as a point. That comes from the original vector equation, evaluated at pi over 4, since that's our t value. So that's why I've written that in right here. I'll actually shift this down just a little bit. And so we can actually find the position as well at pi fourths. So I have 3 cosine of pi over 4, and I have 2 sine of pi over 4. And because it's pi over 4, these values are going to look very much like the other values. And because it's cyclic, because we've got, sine and cosine going on here. So cosine of pi over 4, sine of pi over 4 are both root 2 over 2. So this one is actually 3 square root 2 over 2. And this one is 2 square root 2 over 2. But again, the 2's will cancel, so I'm left with just the square root of 2. And those values are the x1 and the y1. Keep shifting things. So I've got the components that I need to make my parametric equations. So x is equal to 3 square root 2 over 2, and then minus the a value, which is negative 3 square root 13, over 13t. And then the y is going to be square root 2. And then it's plus 2 square root 13 over 13t. Oops. And those would be my parametric equations that I'm looking for. Okay. So it's been a while since we've done the parametric equation part of it, but that's where we came from. Okay, all good so far? Okay. One more topic today, because if you take a look back at the description of our section, it had 2 things, tangent vectors and normal vectors, right? So we're going to take a look at what it means to talk about a normal vector. So far, we've written all our vectors in terms of the standard unit basis. Vectors I, j, k. sometimes other choices are better or more convenient at least. So sometimes other choices are more convenient. For example, for an aircraft, in flight, a better frame of reference will be one that moves with the aircraft. All right, so we talked about the tangent vector, and we specifically talked about a unit tangent vector. We're going to talk about a normal vector, but not just a normal vector, but a principal unit normal vector. Lots of adjectives today. Fancy, that's right. Okay, so here's your definition. The principal unit normal vector, and it's labeled N of t, is the unit vector having the same direction as not our tangent vector, but the derivative of our tangent vector. Okay? And is defined by N of t is the derivative of the unit tangent vector at t. And then we're going to make it a unit vector, right? It says principal unit normal vector. So we have the magnitude of the tangent's derivative. Provided that t prime of t is not 0. I was apparently really into trig because we have another trig example for this today. They are not all trig, I promise. The two that we're doing in class today are. So we're going to find a unit tangent. We've already know how to do that. We just did that. And then we're going to find our principal unit normal vector. So those are our direction sets, or set of directions, I guess. So find the unit tangent and principal unit normal vectors at the given t. And what we're looking at for our position vector is similar to what we had before, 2 cosine t, 3 sine t. Same song, second verse. But we're going to work this at t equals 0. That's going to be friendlier than t equals pi over 4, actually. Okay, derivatives. We've already done a derivative quite like this one. So what is the derivative of this position vector?
-2 sine t, 3 cosine t.
Excellent. And we're going to be taking derivatives of derivatives, so you can't just evaluate at this point. We have to keep going. So if we were just stopping at this point, that would be fine, and we will find this at the value 0 in a moment. But we're going to go ahead and find the magnitude of this, and then we're going to be using that vector to find our principal unit normal vector. So let's go ahead and find the magnitude of r prime of t. So to find the magnitude of this, we would have the square root, and we're going to have some trig going on. We have -2 sine of t squared, and then plus 3 cosine of t squared. So I'm going to get 4 sine squared t and 9 cosine squared t. And there should be like this sort of aching to simplify this a little bit because you see some things being squared. Jubal says no desire to do so at all. We're going to anyway. So there's a Pythagorean identity that we can use. What is it? Yeah, sine squared plus cosine squared equals 1, but that's not exactly what we have because one of them has a coefficient of 4 and the other one has a coefficient of 9. So what we can do, though, is we can break apart this piece so that 4 of them are what I need, so 4 cosine squared, and then we have our other 5 cosine squared that don't, get consumed in the trig identity. So if I take then the 4 sine squared and the 4 cosine squared and I add them together, what do I get? Yeah, I get 4. And then I have the remaining 5 cosine squared t's left over. That's actually my magnitude in general. So I can find my tangent vector then, my unit tangent vector in general as well then. I would take each of the components that I got from my derivative above, so -2 sine t, and I would divide them individually by the magnitude, which is the square root of 4 plus 5 cosine squared of t. And then we do the same thing with the 3 cosine of t and divide it by the square root of 4 plus 5 cosine squared t. It asks me to do this for when t is equal to 0. That's actually a very friendly value here. So if I evaluate this then at 0, what do you get for the first piece? What happens when I put 0 into the first one?
0.
It's 0 because it's sine. And so I've got 0 on this one on completely. The other one's not quite as nice, but cosine of 0 is actually 1. So the 3 is at the top. And on the bottom, since I've got 1, I've actually got the 4 and the 5, so I have the square root of 9. And if you condense that a little bit, this ends up giving you the unit vector 0, 1. So that's my unit tangent vector, 0, 1. Obviously, we're not taking the derivative of the 0, 1, right? We're supposed to be taking the derivative of the generalized tangent before we evaluate it out. That's our next step. And that's not very pretty. So I'm going to go to the next screen, but this is actually what we're trying to take the derivative of next. Right? Ooh, it's fun. Okay, so it's a mess. It's an absolute mess. It's a repeated absolute mess because they're almost the same, the two components. I mean, the numerators are slightly different, but they're similar. So as we find the derivatives of these pieces, there's going to be some repetition going on here. So I first need to find the derivative of t. And so when we evaluate this, when we take the derivative of this, we have a quotient rule, right? And inside of our quotient rule, we have a chain rule as well, right? Because the denominator's got a chain in it. So the quotient rule says I take the denominator So I've got the 4 plus 5 cosine squared t times the derivative of the numerator. So the derivative of my negative 2 sine t is what? Negative 2 cosine of t. And then I'm going to subtract the numerator, which is negative 2 sine t. And I'm going to multiply that by the derivative of the denominator. Well, the derivative of the denominator is the chain rule part, so I have the 1/2. And then I have the 4 plus 5 cosine squared of t to the negative 1/2. And then chain rule says to do the derivative of the inside. Well, the derivative of the inside is another chain because it's cosine squared. The 4 plus goes away. Or the 4 addition at the beginning goes away. The 5 stays. So the 2 will come down with the 5. The derivative of cosine would be negative sine. So I'm going to get a negative as I do this. So this is going to be negative 10. I rewrite my cosine. Oops, that's not cotangent. It was, but it wasn't supposed to be cosine t. And then sine t, because the derivative of the inside would be, the derivative of cosine would be negative sine. So that's where my negative is coming from. All of that is over the denominator squared, but the denominator is a square root denominator, so the denominator squared part's nice, right? So this denominator for the first component, and for the second component as well, actually, is going to actually just be 4 plus 5 cosine squared t. And this is the first half. The second half is so similar, though, right? The only pieces that are going to change on the second half are these two pieces. Everything else is going to remain the same. So as you're sort of looking at your own writing, just write your own pieces down. You don't need to keep looking back at my screen. The rest of it's going to be the same, just those red pieces are going to change. So I'm going to rewrite those pieces as well. I've got the square root of the 4 plus 5 cosine squared t. I need the derivative of the second numerator, so the derivative of 3 cosine t, which is actually negative 3 sine t. And then I've got subtraction. And then I've got the rewriting of the second numerator. So that's the 3 cosine t. And then the rest is the same. I have 1/2. I have the 4 plus 5 cosine squared t to the negative 1/2. And then I have the times negative 10 cosine of t sine t. And it's all over the same denominator. Four plus 5 cosine squared t. Okay, so here's the good news, though. The whole point of this is that we're going to be evaluating it, right? We're evaluating it at t equal to 0, so it's not like I need to clean this up. I'm not trying to keep this generalized. I'm trying to evaluate this. So there's no need to continue on much further at this point with trying to clean things up. We're going to figure out what this is at 0. This is kind of like what happened over here on this one, though the problem itself was much easier. I evaluated it, and then I took the magnitude, right? I don't need the magnitude of what I just wrote down. There's no need for that. I need the magnitude of it evaluated at t equal to 0. So we're at that point. So we're going to evaluate t prime of 0. Okay, so t prime of 0. The pieces where I put in 0 for the cosine all become 3s, right? So this piece is a 3, and this piece is a 3. Yeah? Are those 3s? Yeah, because it's going to be the square root of 9, because cosine is going to be the 1. So I'm going to get 3s out of those. So I have a 3 for the first one. What is negative 2 cosine of 0? That's negative 2. Whoops. And then the rest of it, the entire rest of this piece is going to be what?
0.
It's going to be 0 because I've got a sine of 0 being multiplied, and sine of 0 is 0. So the entire numerator is negative 6. Yeah, it's negative 6. And the denominator is going to be what? 9. Because it was the same 3, but it's not got the square root anymore, so now it's just 9. So this is the first piece. The second piece also has a denominator of 9. So let's take a look at this one. This one has a 0 right here, because there's the sign of 0, so this whole thing is 0. But what about the second piece? It's also 0, because there's a sign of t right here that's, again, being multiplied by everything 0. This whole thing's 0, so the whole thing here is actually 0. So while I do have a denominator of 9, it's sort of irrelevant. So when I multiply 3 times negative 2 divided by 9 and I simplify, what do I get? Negative 2/3, and then my second component is 0. And I don't know that you need to actually do a whole lot to tell me what this then is, but what's the magnitude then of that?
Negative 2/3. No, 2/3.
Yeah, it's 2/3, right? Magnitude means the length, and it's got a 0 in one direction. So the magnitude of this is actually 2/3. So when you think about finding the principal unit normal vector here, 0. This is the vector negative 2/3, 0, and it's divided by 2/3, right? We've made it into a unit vector. It's the unit vector negative 1, 0. So as atrocious as it is for the middle part, it actually cleans up fabulously at the end.
Because we chose t equals 0.
Because t equals 0 is what was given to us. Yes, exactly. If it had been pi over 4, it would have been ugly, wouldn't it? It would have. It would have been really ugly. Yeah, you're right. Okay, so you want to know the best news for the day? Short homework, that's right. It's 6 problems. 6. But they're kind of long. I mean, right? Like this is not necessarily as short as some of the other things we've done because the problems themselves are a little longer. So this is page 852. It's numbers 5, 6, 10, 13, 16, and 17. All right.